Okay, we were talking about the advantages of position tolerances over coordinate tolerances. Um, Position tolerances clearly have a better definition. Um, and we pick up this bonus tolerance here, so additional tolerance is available. So coordinate tolerance is you have a square or rectangular. This is determined by plus or minus tolerances. But when we go to GD&T, we use a positional tolerance. And then we define that positional tolerance to be a diametrical shape. And so therefore we pick up a little bit more area. But to me, that's not the biggest thing. The biggest thing is right here. Coordinate location tolerances are ambiguous. Okay, so if we took our drawing and we draw it up like this, we're used to seeing this way. Okay, so we've got the surface. We're going to locate these holes here, 0.375 from the edge. Okay, so how are we going to spec the location of these holes? Okay, so what we would do typically is you take a vernier caliper and we measure from the edge to the edge of the hole. But really, what are we getting? Okay, because there's surface variations on the edge of the part where we're checking it. We're not picking it up as a datum. We're just picking it up at one point. That's shown right here, the 490. We're picking up the 490 at this one point. We're not considering the high points and the low points and the 2 points that define this datum simulator. We're just picking up this one point here. Okay, and then once we start measuring from hole to hole with our verniers, are we getting this off location? Are we getting it at an angle? As you can see, the position tolerance that we use in GD&T, because we're going to check it back to these datum simulators. This is not a good way to dimension these holes because you're not going to be able to check them. Okay, because you're not going to come up with a faithful measurement of whether these holes are in or not. Okay, so position tolerances, by the way, are very definite. Okay, so when I'm checking these locations for this, I've got these basic dimensions back to these features here. I'm checking it using a datum simulator. I'm simulating datum A, I'm simulating datum B, I'm simulating datum C, and I'm checking the location of these holes faithfully and on position. Okay, so that in a nutshell is the advantages of using positional tolerances versus coordinate location tolerances. Okay, position calculations from coordinate measurements. You can get measurements automatic or manually measured. Measurements are made relative to datum reference frames. A feature's measured location coordinates are used to calculate the whole location distance from its specified true position coordinates. And this distance is compared to the positional tolerance to verify compliance to the requirement. So our positional tolerance variation is going to be, this is taking this, we're going to calculate how far the hole is off relative to its true position. And then to find out what its diameter position variation is, we take that radius and essentially square it and then come up with the diameter position variation. This one over here, we're going to talk about counterbore holes. You really have three methods. Okay, so counterbore hole may be machined in a different setup, therefore may not be perfectly concentric to the hole. So if we have a counterbore hole, we got three ways to dimension those counterbores for location. One is to have a position tolerance to control both the hole and the counterbore. Two is we have separate position tolerances for the hole and the counterbore. And thirdly, we could have a counterbore position tolerance referenced back to the hole location. And I'm going to show you each one of these three. First of all, let's do the one position tolerance to control the hole in the counterbore. Okay, so here we have our counterbore call out, we have our hole size, we have our counterbore call out, and then we have our true position. Now what that means is we're establishing a true position zone centered on the true position, and the counterbore and the hole have to be within that true position zone individually, even though we have just one tolerance. That's what that one means. Here we have separate position tolerances for the hole in the counter bore. Okay, so here's our hole, and then we put a position tolerance on the hole, and then here's our counter bore, and then we put our position tolerance on the counter bore. Notice that we're using a greater tolerance zone for the counter bore, but we are using the same datum reference frame A, B, and C. Now this one, last one, what we're doing here is we have here's our hole, here's our true position of the hole to our datum reference frame A, B, and C. And then here's our counter bore call out, and then we have a separate feature control frame on that back to D, D being the hole. Okay, so 4 places individually, we're going to be checking the location of the counter bore with respect to the hole. Now threads. When you're applying a positional tolerance to a thread, it is assumed that the positional tolerance is applied to the axis of the pitch cylinder. Okay? So what we have right here, we have a threaded hole, we have a feature control frame for its location, we have an MMC modifier on the location. What that means is we have no notation here. That means the tolerance is applied to the pitch diameter by default. Okay. However, if we came back and specified minor diameter, then we have to note it minor diameter. Okay. Otherwise, it's going to default to the pitch diameter. Projected tolerances zones. Okay, so we have this hole, this threaded hole, and we're going to put a projected tolerance zone specification in here. And what that does, it projects the tolerance zone up above the part, in this case a 1/2 inch. So we have this 18 thousandths, and it's projected upwards from the surface of the part by a 1/2 inch. That's one way to dimension a projected tolerance zone. Here would be the other way, where we take a dimension of a 1/2 inch and we put the projected modifier here in the tolerance, but we don't put the value of the projected height into the tolerance. Like we did here, we put the value of 50 thousandths in, the 500 thousandths in this one, we just show a dimension line with that. Non-cylindrical features of size. Those are slots, tabs, and rails. No diameter symbol is going to be used in the feature control frame for the tolerance zone shape. Do not place the feature control frame on an extension line. And it defines the total width of the tolerance zone. Okay, so in this case, we have a slot. Okay, we have 2 dimensions on the slot. We have the height and we have the width. Each one of these has its own tolerance zone, and it's at MMC. And here's what that zone means. In the vertical direction, we have 14 thousandths. We have a 14 thousandths wide tolerance zone for that slot in that direction. And then we have a 60 thousandths wide tolerance zone on this slot dimension in this direction. And then finally, non-cylindrical features of size. We're going to put a true position on this feature of size here. And what that means is the center plane of the slot cannot vary in position by more than 16 thousandths when the slot is at its MMC. And this is similar for a key way. Okay, this concludes the Chapter 8 lessons